Okay, so in this video, we are gonna see about Euler theorem. Euler theorem, I'm gonna write the statement, but the same thing, it is actually number theoretical theorem. But here, what we are gonna do is we are gonna take that concept and we are gonna prove using group theory. So this again comes under abstract algebra or modern algebra. In the proof technique, I'm gonna go with group theory concept. So now, let me write the statement of it. So basically, I have an integer. Let n be an integer, and I also have another integer such that the GCD of a comma n is equal to 1. That is what I have, and right now I'm gonna prove then a to the power of phi of n is congruent to 1 mod n. So this is my Euler theorem. N is an integer, a is again an integer, and GCD of a and n is 1. Then I have to prove a to the power of phi of n is congruent to 1 mod n. So now what is phi of n? Phi of n is kind of a new term here, no? Phi of n is a number of, it's a number of integers less than n and relatively prime to n. So that is phi of n. For example, if my n is equal to 4, then phi of n is, all we have to do is we have to count the number of integers less than n relatively prime to n. So now 1 is a number that is relatively prime to 4 and 3 is a number that is relatively prime to 4. Therefore phi of n is 2, right? And if you take n is equal to 5, then phi of n is 4 because there are numbers 1, 2, 3, 4, 4 numbers less than 5 and relatively prime to 5. So phi of n is also called as Euler totient function. This phi of n is called as Euler's totient function. Okay, having said that, now we shall look at the statement one more. All we have is an integer and another integer that is relatively prime to 1. That is GCD. Whenever I write this bracket, this is GCD of a and n is equal to 1. Then a to the power of phi of n is congruent to 1 mod n. This is what I am gonna prove. As I told you earlier, so there are so many proofs for this particular theorem. So now right now I'm gonna go with the concept of group theory. So what I'm gonna do is I'm gonna first construct a set. So we are all given with an integer, right? And we are also given with another integer a, and I'm gonna take both of them, and the GCD of a and n is 1. Okay, so these are all the things that we are given with. So right now I'm gonna prove a to the power of phi of n is congruent to 1 mod n. That is my ultimate time. So for that I'm gonna first construct a set G. That is, let me write it here. Let G is equal to. So what I'm gonna do, I'm gonna collect all integers such that the integer has to be less than n and GCD of m and n is equal to 1. So I'm gonna collect these integers such that m is less than n and GCD of m and n is equal to 1. So mathematically this is the way to write it. So formally what we can tell is G is a collection of integers that is less than n and relatively prime to n, right? So now this definition we have heard right now, no? Phi of n is the number of integers that is less than n relatively prime to n. But the set that we have constructed is a actual collection of integers that is less than n relatively prime to n. And this G under multiplication modulo will be a group. You can verify this later on. If you have any doubt in that, you can ask me in the comment section or else you can directly ask me. So G comma dot circle, the multiplication modulo is a group. So now, having said this, we shall actually try to find the cardinality, that is order of this particular group G. So I told you G is a collection of integers less than n relatively prime to n, and phi of n is the number of integers less than n relatively prime to n. So obviously the order of G, the number of elements in G is equal to nothing but, can you think for a second? what is this? Nothing but phi of n, right? So, okay, fine. And we know that, okay, that we will discuss. Now, we are also given with an element in Z. A is an integer, no? So, now, and what is the relationship between A and N? GCD is 1. Okay, so now let me divide A by N. For any two integers, we can divide it by that one by another, and we can write it in this form. A is equal to Qn plus R, where R is a reminder, R is an integer first, and then R can be, this is the usual 0, or can be 0, or can be less than n. The range is 0 less than or equal to or less than n. Now listen, so we have here GCD of A and N is equal to 1, right? So if R is equal to 0, then in that scenario A is equal to Qn. That means that A is equal to Qn, no? So what does it imply actually? This imply n will divide A, right? N will divide n, because A is equal to Qn, n will divide A, and n will divide itself, no? Therefore, GCD of A and n is not equal to n. Greatest common divisor of A and n is not equal to n, because we have a number that divides A as well as we have a number that divides n. Therefore, this is a kind of a contradiction, because we have assumed R is equal to 0. If R is equal to 0, what we are getting contradicts the fact that GCD of A and n is equal to 1. Therefore, R cannot be equal to 0, which means A is equal to Qn plus R. Here, R cannot be equal to 0, which means 0 less than, strictly less than R and less than n. So, right now we have this. Okay. So, now, what is this now? A is any integer, but R is an integer that is less than n. And moreover, if you find the GCD of R and n, that will be equal to 1, right? Okay. And you have to assume here, since GCD of A and n is also 1, and we have R is a value that is less than n. So having these two combined, we also have R comma n. We will be having GCD of R and n is also equal to 1, right? So suppose if you have still confusion with this, we shall figure that out. How the GCD of R and n is equal to 1. If you still wondering how this is, okay. So let me take, if the GCD is not equal to 1, let me take this as some D, where D is greater than 1. Let me take like this. Then what does it mean? If GCD is D, D is the greatest common divisor, no? Therefore, D should divide R and D should divide N. That implies D should divide Qn plus R, any multiple of Q and then plus R. What is this Qn plus R? Qn plus R is A, right? Therefore, D should divide A. 1 second. Yeah. D should divide A. So, now we have D is dividing A and D is dividing N. Therefore, GCD of A and N it is not equal to 1. It should be, it is greatest common divisor. So, if D is not the greatest, it should be greater than or equal to D. GCD is greater than or equal to D, and where D is greater than 1, right? So, this is again a contradiction, because GCD of A and N is equal to 1. So, we are arriving at a contradiction because of the fact that we have assumed R comma N, GCD of R comma N is equal to a number that is greater than 1. So, therefore, this case cannot happen. Therefore, GCD of R comma N also should be equal to 1. So, now we will write step by step what are all the things that we have done so far. We have constructed, we had first two integers, remember this, and GCD of those two is equal to 1. And after that, we have constructed a set G, and we proved this is a group, right? That's it, under multiplication modulo. And then what did we do? We have written this as A is equal to Qn plus R, and we talked about R, and the R is less than N, and R comma N is equal to 1. So far we have proved like this. That's all. So now I want you to have attention on this R. What is R? R is a integer first. And what is R again? R is less than N. And moreover, R is relatively prime to N. So this is an element or an integer that is less than n relatively prime to n. Therefore, of course, in this collection, R will be a member. In this collection, R will definitely be a member. That is how the set group is constructed. Therefore, R will definitely be in G. Right? And we have also one theorem that tells us, one second, give me one second, let me change its color. Yeah, great. Okay. So now we have a theorem that tells a to the power of order of G is equal to E for every element of G. This is another statement that you have to remember. A to the power of order of G is equal to identity for every element in G. So now we are not sure whether A that we have had in the very beginning is an element of G, but we are very sure that my R is an element of G. Therefore, R to the power of order of G is an identity. What is the identity in respect to that? It is equal to 1. What is order of G? We have just now told the order of R to the power of I of n is equal to 1. That actually R to the power of I of n is equal to 1. Right? Okay. Okay, so now what is A Qn plus R? Okay, fine. So now, yeah. So now this is A to the A, if we divide it by n, we will be having the remainder to be R. That is, A is congruent to R mod n. That is what we have, right? Okay. So if A is congruent to R mod n, then A to the power of I of n will be congruent to R to the power of I of n mod n. What is R to the power of I of n? R to the power of I of n is 1. So A to the power of I of n is congruent to 1 mod n. Yeah, that's it. We proved A to the power of I of n is congruent to 1 mod n. That's it. This is Euler's theorem. I'll repeat the statement one more time. We had two integers a and n, and GCD of them is 1. Then A to the power of I of n is congruent to 1 mod n. So for this, we have constructed a group, and we are not sure whether A that we had is an element of G, but therefore we found out an element of G, that is R, and we proved R to the power, we use this property R to the power of order of G is equal to the identity element. Order of G is phi of n and E is 1, and we kind of use this in order to arrive at this result. Okay, I hope this will help you. If you still have any doubt, let me know so that I will be able to help you. Thank you. One second.